Yeah, hi. This lecture is on simple linear regression and correlation, and you can see that quite few topics we want to cover in a series of videos. Uh, uh, Actually, the first five of them, and the sixth one is the computer print, and the last three, just I'm gonna skip over those. So let's start. What is linear regression anyway? So linear regression by definition, is a statistical technique used to predict or forecast the value of a variable from known related variables. Okay, so let's go over this example here. See if that helps with illustrating all the idea. So we have a problem. We want to predict monthly sales Y for a company where there's not much seasonal variation, so we're not going to be worried about seasonality. For the predictor variable X, we use the amount spent by the company on advertising. So we relate advertising to sales volume. We want to see whether advertising really affects sales. So we wish to determine whether advertising is worthwhile. That is, whether advertising actually related to the firm's sales volume. In addition, we want to be able to predict future sales volume from the amount of money we are willing to spend on advertising. So here we have data from 10 randomly selected previous months, and let's go over the data. So the first one is this just list of months, and here X is our sales, is our advertising amount, and Y is our sales, and they are in tens of thousands of dollars. So in the first value here we spent $12,000, we had $1,010,000 in sales, $8,000 we had $920,000 in sales, and so on. So this is our data. And so I'm going to see if in the future I spend $10,000 in sales, what would be my if in the future I spend $10,000 in advertising, what would be my sales volume? Are they related? Will there be that relationship? So this is not just, I just want to point out that this data can represent some other types of problems. So I can say X is the amount spent by a company on preventive health care, and Y is the savings, and so on. So you can think of many other problems. So we're going to have some definitions here used in regression analysis. Regularly people use response or dependent variable of interest. It's Y, or sales volume in our problem. The independent or predictor variable is our X, how much we spend on expenditure. And we assume there's a linear relationship, that is a straight line equation, but we know that Y equal A plus BX is the equation of a straight line, where A is the intercept and B is the slope. So how would this data fit into an equation of a straight line? And the answer, it doesn't. So so let me jump ahead and show you, if we're going to graph this data, to do something called a scatter diagram. And using that scatter diagram, I'm going to do a best fit line and then find the equation of that best fit line. So that's a lot of work here, and so that's what we have. So we have our data is here, these red dots. So this is from Minitab. So when I spend $6,000, I get this much sales, about what, probably $760,000. When I spend $9,000, I get about $900,000 in sales, and so on. So we get all these data. So you can see that data is not linear; they don't fall on a straight line. So we are fitting a trend here. The trend seems to be going upward, a linear upward trend. And if that's the case, we call that that's why we call it a linear regression. And then we're going to fit a straight line through the data. We're going to call that the best fit line. And we want to find out what are those parameters of that line, the slope and the y-intercept here. So that's going to be the bulk of our work on the regression. And once we get that line, say if in the future month I want to spend 10,000, I can just go up there, read the sales. Of course, we know that will give us an estimate or prediction of the sales volume, but we also like to get a margin of error and confidence intervals and so on. And we're gonna probably not get into that at this point. Okay, so how do we get that best fit line for the data? First, we're gonna assume we have a linear probabilistic model, which we call y equal beta 0. So that's beta 0 plus beta 1x plus an epsilon, a random error. So that's the first part, is similar to the equation of a straight line, except these are unknown parameters, and x and y are random variables. And epsilon is the factor, this is called epsilon. It's a random error because whatever x is, whatever money I spend on advertising, if I spend 10,000 in 2 months on advertising, the sales are not going to be exactly the same. They're going to change. So there's this random factor that represents other things that affect sales, like price, health of the economy, competition, and so on. So all of these are called the random error due to factors not included in the model, or called unexplained factors. The model doesn't explain them. So we collect them all in this little epsilon thingy. So the assumptions is that epsilon, which is a random variable, has a mean 0, has a constant variance called sigma square, and has a normal distribution. Now further, we assume that any two y values for different x values would be independent of each other. So these are just basic assumptions all regression models need to have. And now I want to find beta, the estimate. We always put a hat for estimate, so beta 0 hat and beta 1 hat, and y hat would be the prediction of y for a certain level of advertising. So this is called my estimated regression equation, or prediction equation, or least squares prediction equation. So it's a very important equation. That's why it has many different names. And the way we are going to do it is this. We're going to take y, this y here, and the data for each one of these, and look at how far it is from y hat, the predicted value, the one on the real line, the regression line. Square that and add all of these, and then minimize that. And in doing so, we will be able to get those estimates. So let me jump ahead. So basically what we will be doing here is this is my y, and the value on the, if I go up, continue up, that will be y hat, the value on the yellow line. Same thing here, I'm going to make another line here. These are called the errors, basically. How far are these points from the prediction line? Square that difference and add them up, and I want to minimize them, which basically keep moving that line and keep recalculating those errors, add them up until I get the smallest possible value. And once I get that, the corresponding parameters would be my best fit equation, or will give me my best fit equation. Okay, so that's the idea. Now if I do that, here is how would I get all these values. How would I estimate? So now I want to estimate beta 0, beta 1, and sigma square. Sigma square represents how far or close those points to the lines. If I have points up there and points down here, my sigma square would be large. If the points are closer to the line, my sigma square would be smaller. So it tells me how spread those points around the line. Okay. So now x bar is, of course, I add all the x values, the advertising divided by n. Y bar, I add all the sales volume divided by n, so I get the x bar and y bar. And now I want to get those values here. I call this SSXX, which is basically the sum of squares of the deviation. So this is how much x deviates from x bar. I square that, add them up. So these are called sums of squares of deviations, and you've seen that in the definition of the sample variance in data analysis, but without dividing by n-1 here. And that's the computational version of it. So it's easier to work with the second one. That's for y, same thing, sums of squares of deviations for y. And that's a change in y caused by the change in x. So this is x minus x bar, y minus y bar. So you take one from here, one from there, and add them up. And this would give me the computational version of it. And so once I get those values, I can get beta 1 hat as the change in y caused by x. So this is the sum of squares of deviations in y caused by x over the sum of squares of deviations in x. So the slope, change in y over change in x. But now it's more involved than the simple one you knew before. And beta 0 hat I estimated as y bar minus beta 1 hat x bar. So to estimate sigma square, I take SSYY, this one here, minus the beta 1 hat times SSXY from here. And once I get that, I divide it by n-2 to get S squared. And that's my degrees of freedom here, because I estimate 2 parameters, so I get 2 degrees of freedom here. Okay, I lose 2 degrees of freedom, so I get n-2. So beta 1 hat is the slope of the estimated regression equation, and S squared, we said, is the spread of the points xy around the regression line. So the first question usually in a problem like this, once you have the data, is do a scatter diagram. Can you say that x and y look linearly related? And so if you look at this, you draw all these red dots, and then we look, yeah, there's a linear, upward linear trend in this case that we can fit to the straight line. Second question, can you use the computational formulas to provide a data summary? And this is the data summary we have. X bar 0.94, y bar 95.9, and I want this x as sum of square of deviations in x, sum of square of deviations in y, and the ones in y caused by x. So what you need here to get column x, y, x squared, x, y, and y squares to get to use the computational formulas. So these are my x values, we had them before. These are my y values. Now I square x. So what I have here is the square of each one of these values. What I have here is this value multiplied by the corresponding y value, and what I have here is the y values squared. So if I sum all of these, what I have here is sum of all x values, sum of all y values, sum of all x squared values. This is the sum of xy, and that's the sum of y squared values, and that's the totals here. So I can get here x bar, the total divided by n is 0.94, and y bar is 95.9. Now the SSXX, I got, so sigma x squared, that's from here, minus sigma x squared. So which means here first add 10 square. That's when I added 9.4, b squared divided by 10. I got the answer here. The SSXY, I have the formula, so sigma xy comes from here. Sigma x is the 9.4 times sigma y times the 959 divided by n, which is 10. Simplify, get the answer here. And the SSYY, similar to this one here, so I get sigma y square is this number here, goes there, sigma y square, so that's my sigma y. I square it, divide by 10, I got this number here. Alright, so now I got the data summary, so I can estimate beta 0 and beta 1. I start with beta 1 hat, now we call them hats because they are estimates. SSXY over SSXX, so it's this quantity over xy, it's the 2334 over the 0.44. Simplify it, and you always should keep as many decimal places as you want, but at the end you can just keep 2, that's fine. So beta 0 hat is y bar minus beta 1 hat x bar, the formula we had, we substitute here. So y bar is 95.9, beta 1 hat is 52.5676, and note that I use the one with the more decimal points because I'm doing intermediate calculations. I can only round at the end, which is fine. And then y x bar is 0.94, so I get this is the y-intercept. I also can estimate the sigma square, so SSE, I have these values already, and divide by n minus 2, which is 8, that gives me 4675. So that's a measure of my variability. Now I find my least square line for the data. I know my equation should be y hat beta 0 hat plus beta 1 hat x, so it's going to be substitute 4649 plus 5257x. So that's basically what it is, and I got my regression line or estimated regression equation or prediction line, whatever you call it. Now I can use it for predictions. So predict the sales volume y for a given expenditure level of 10,000. Of course, we used in here we used everything is in tens of thousands, so that means x equal 1. So if I substitute x equal 1 in the equation here, I get y hat equal this plus this x, and I want to replace x by 1 and add up, so that's 99.06. Now I have to remember to multiply this by 10,000 to get my sales volume of $990,600. So this is predicting y. So if next month I want to spend $10,000, what would be my predicted sales volume? Sometimes I may be interested in the expected sales volume. If I plan to spend $10,000 every month for the next 15 months, on average, what would be my sales volume? So that's question 7. So that's the mean sales volume. And it's actually, the answer is the same, you can see here. So whether you are predicting the sales volume for 1 month or for the average, the answer will be the same. What will change really, however, is the bound on the error of estimation, and that's going to be given later on in these notes. And so when you compute confidence intervals, the confidence intervals will be different. Okay. We go over the coefficient of correlation. So now we found the linear relationship between x and y. We want to know how strong is this linear relationship between x and y. And the way we measure that is by something called the coefficient of correlation. It's called R, which is the change in y caused by x over the change of x times the change of y, or the total change, and we take the square root of that. And if you do that, so it's basically a R is a normalized slope, so it can't be less than -1 or larger than 1. So the population coefficient correlation, we call it rho. The sample correlation is called 1. R greater than 0 indicates positive correlation, like when the slope is positive, so you have an upward linear trend. If R is negative, that indicates a negative correlation, similar to having the slope being negative, so you have a downward trend. R equals 0 indicates no trend. So but if R is like 80 or 90, that means it's very strong. If it's around 40 to 60, we say it's moderate correlation. If it's below 20, we say it's very weak correlation. Okay, so that's another way to look at this. So in my example, if I were to compute R, it would be We calculated this as 23.34, and this is 0.44, and this is 1600.9 with the square root. So that gives me 0.88. So that's a very strong correlation between advertising and sales volume. Now, if I were to do some, if I were to square both sides here and do some algebraic manipulations, I would find out that r squared equal this minus this over this. And let's look at this. So that's the total variability in y minus the error, which is the unexplained factors, over the total variability in y. So that represents, so if I take the total explained, the total variability minus the unexplained variability, so that's the explained variability, and over the total variability, so that's the percentage of variability explained by this correlation. And so that represents really the, if we had a question like percentage, by what percentage is the sum of squares of deviations of y about the mean is reduced by using y hat rather than y bar as prediction of y. So when I use y hat, I'm using x as a predictor versus just y bar, ignoring advertising. So if I use advertising to predict sales volume, I'm trying to it explains 88% of the variability in sales volume. So that's basically, or 88 square, so that's 77% of my sales volume. So that's pretty high, okay? And that's all about regression analysis. The next video is going to be how to use analysis of variance to understand, also to test the validity of the regression model.